Hello. So this presentation is on WireGuard, which is a new secure networking tunnel to replace IPsec, OpenVPN, and all the other VPN networking tunnels that have been around before. So to get started, who am I? Jason Donenfeld, also known as ZX2C4 on the internet. I'm the founder of Edge Security, small security consultancy. Usually, my background has been in exploitation, vulnerability analysis, finding 0 days, penetration testing, but not so much in networking. But somewhat recently, for some infrastructure, I wanted to run some secure networking elements, and the existing solutions were just too bad. Overly complex, impossible to audit, just not something I could really depend on in a secure setting. So I set out to make WireGuard, which is vastly simpler. So WireGuard is a layer 3 tunneling protocol, which is both IPv4 and IPv6. It doesn't do layer 2. It'll never forward Ethernet frames. It's just IP. And there aren't any plans ever to include something other than layer 3, because I think that's the right way to do things securely. And rather than existing solutions which support tons of different options for every type of network, WireGuard supports what I consider to be the best way. And the idea is to change your infrastructure to fit the tool that does things right. So in that way, WireGuard is extremely opinionated. But I think for many, this will work very well. It lives in the Linux kernel, so that it's very fast and well integrated. But we're developing cross-platform solutions in languages like Go, Rust, Java, etc. It's also UDP-based, so we can achieve high performance. But we've got some good tricks to punch through firewalls. We use some modern cryptography. Existing solutions like IPsec and OpenVPN use crypto mainly developed in the 90s, and it's been a while since then. And as I said before, we're really focusing on making things as simple as possible, clean concepts that you can understand, and clean code that an individual can read and audit in a day. The authentication model, we get rid of all certificates. There's no X509, no ASN1. They're just short public keys that can be passed around, copy and pasted, and it works just like the SSH model. You have an authorized keys file, you share your keys, and then you have a secure network tunnel. Okay, so this first security design principle is easily auditable. Just to compare things, OpenVPN, it's 100,000 lines of code, but then you also need OpenSSL, which is another 500,000 lines of code. So it takes a big, big team to audit that, and we've seen problems in the last several years. Linux XFRM, which is the IPsec in the Linux kernel, is about 14,000 lines of code, but that doesn't even include the key exchange, which is the most difficult part. And for that, usually people use something like StrongSwan, which is 400,000 lines of code. So again, this is overwhelming. Soft Ether is one of these VPN solutions that supports every protocol, IPsec, OpenVPN, a couple Microsoft ones. And this is 330,000 lines of code. So again, super complex. WireGuard is less than 4,000 lines of code, which means that any one of you could read the entire code base in a couple hours pretty easily and be reasonably sure that it's secure, that you've understood how it works. And of course, the more eyeballs on it, the more bugs we'll uncover. And I think WireGuard should get to a point where we're extremely confident in the security of the code, way faster than OpenVPN or IPsec, which we may never get to a point where we can really trust something that huge. So just to put it in the solar system of VPNs, WireGuard is the Pluto, if you will, of VPNs, just a tiny little speck in terms of lines of code. The second principle is simplicity of the interface. We don't want a super complicated configuration. We don't want to have to do anything that's out of the ordinary with the normal networking tools and setup that you already know about in order to make a security tunnel. So with WireGuard, you just get a normal network interface. And you can add it using the normal Linux IP route 2 tools. So IP-link add WG0 would add a WireGuard interface. You can give it an IP address. You can add routes. You can even use legacy ifconfig if you want. And it works with IP tables. You just give it -i and then your WireGuard interface. And if a packet comes from a WireGuard interface, you can be sure that it's actually secure. So a super simple interface using the same tools and methodologies that you already know about. And of course, bind works in the way you want. So if you bind to an IP address that belongs to a WireGuard interface, that socket will then become secure. So this is, in a sense, sort of blasphemous, because in achieving this simplicity, we've done away with all of the academically pure layering assumptions. IPsec was created by a big committee of experts, super smart people, and they all really cared about doing things pure, kind of architects of the internet type of people. And while they came up with something that might, in some academic realm, be really nice, in practice it winds up being super, super complex, nearly impossible to deploy, and just a mess. IPsec has a transformation table for outgoing packets, key exchange is some other user space daemon. It's just really overwhelmingly difficult. And so WireGuard, we just get rid of all these layers. Instead, you just have the interface, the simple network interface. And with that, with getting rid of the layers, in fact, we run into problems because we have layering violations. And so WireGuard starts with the simple place we want to go, the interface, and then tries to find clever engineering and cryptography solutions to actually achieve that. Okay, so the fundamental idea that makes this possible is called crypto key routing. And what this means is a VPN is fundamentally a relationship between a peer, which is identified by its public key, and a list of IP addresses that that peer is allowed to be. So it's just a mapping. We have keys in one end of the table and IP addresses in the other. So what this means is that a WireGuard interface has its own private key. It has a eliciting UDP port, as we mentioned, it's a UDP protocol, and it has a list of peers. Then each peer has its public key, which is identified by, and then it has a list of its associated IP addresses. Those are IP addresses that are inside the secure tunnel, IP addresses that will definitely be secure IP addresses. And optionally, it has the endpoint IP and port of the UDP socket that's listening on the other end. So if we look at the config file here, this is just a very simple format, like Windows ini, for example. And a server, we see over there, has a private key and a listening port. And then this one has two peers. Each peer has a public key. And each peer has a range of IP addresses that that peer is allowed to be. Then a client is much simpler. It also has its private key. And it only has one key, peer, which is the server. And its allowed IPs are everything, because say it's an internet access server, and so it wants to allow that server to send it any IP from anywhere on the internet. And finally, it gives the endpoint of the server. And so that's it. That's it for the configuration. You provide that to a WireGuard interface, and you have a secure tunnel. So how does this actually work in implementation? A user space program sends a packet using normal send syscall. The ordinary Linux routing table then gives it to the WireGuard interface. At this point, it's our code that's running. So WireGuard looks at the destination IP of that packet and says, are there any peers in the crypto key routing table that have that as an allowed IP? So if we go back to our table here, let's say user space sends a packet to 10.192.122.3, then it'll use this peer. At that point, the packet is encrypted with the current session keys for that peer, and it's secure, authenticated, etc. On the receiving end, it works in the opposite way. The UDP socket receives a packet. It decrypts the packet, and when it decrypts it, then it learns, okay, it's from this peer with this public key. It then looks in that same routing table and says, okay, does this peer have in its allowed IPs that IP address? Is this peer allowed to actually be sending packets as that IP? And if it is, it accepts it. If it's not, it's dropped. So for configuring this, we have a very simple utility called WG. At some point, this utility will hopefully be integrated into the normal IP, but for now it's called WG. And we can call set with it, setconf and getconf for configuration files. We can generate new keys in a secure way. We can derive public keys, etc. And so it's just a normal command line interface like you're used to using with pretty ASCII colors. And so all of this makes system administration very easy, much easier certainly than OpenVPN or IPsec. You can make rules like if it comes from interface WG0, WireGuard interface, and it's from, say, 192.168.517, then it definitely came from, say, Yoshi's tunnel if it's from that IP in that interface. You have definite assurance. So you don't need any complicated firewall marks, secure marks, any of that old terminology. If it came from the interface and it comes from the IP you have in mind, then it's been securely transmitted and is authentically from the sender. And so without even really thinking that hard, you might be able just to imagine the actual IP tables rules for this kind of thing. It's very basic. Okay, so just to recap here, the simplicity gives us a stateless interface. You give the WireGuard interface the peers, and that's it, then you send packets. It doesn't appear to be state to the user. And endpoints roam, which is a nice feature. If you suddenly change IPs, like you put your laptop to sleep in the hotel, you come to the conference, you open it back up, you're already connected. There's no reconnection necessary. It just works. So it's sort of like Mosh, a tool that you might have seen before. And so all the other internal bookkeeping is completely invisible to the admin. And we'll go into that in a bit. Okay, design principle number 3. This is sort of a defense in depth coding perspective. First of all state that we require in WireGuard, all state variables are allocated during configuration, not during the actual exchange of packets. Finally, no memory is even dynamically allocated in response to any received packets. So this eliminates a huge class of bugs. Takes away all sorts of heap vulnerabilities that typically come up, misallocations, error handling, and is also very good from system resources perspective. All packet headers have fixed widths, so there's no parsing involved. You know that the next field is going to be this many bytes, and so you just indiscriminately read that many bytes. So again, we have necessarily no parser bugs because there are no parsers. And then finally, we don't modify state ever in response to a packet that's unauthenticated, so that there's no avenues by definition for an attacker to modify some aspect of the program before it has authentication in order to gain authentication. So just with kind of basic principles like this, we eliminate a huge swath of attack surface that ordinarily would come up. Okay, finally we get stealth. And this is important to me. As I said earlier, usually I do exploitation, vulnerability dev, and I worked for several years on a kernel rootkit. And so one of the things you need with a rootkit is a secure, stealthy exfiltration mechanism. And the ideas for WireGuard actually stemmed out of this offensive perspective. And so now I've taken that general idea and put it into WireGuard, which is fundamentally a defensive solution. And what it amounts to is that WireGuard should never respond at all to any unauthenticated packets, so that you don't know it even exists. You don't know that a port is listening. You have absolutely no insight as an attacker that anything's there. And so if you run this on an edge machine that has no other ports listening, it's impossible to even determine that that computer exists on the internet because you have WireGuard only responding to authenticated packets. If you have a man-in-the-middle connection or position and nobody's talking at the time, you also don't get any indication that something's there because it's not a chatty protocol. When peers have packets to send, they send them. When there's nothing to send, it goes to sleep and nothing's sent at all. So again, this comes from the requirements for a rootkit for an exfiltration mechanism, except it turns out that these offensive techniques are super useful from a defensive perspective too. Okay, and finally, we need solid crypto. All of this would be worthless if the crypto wasn't good. And so we make use of what's called the noise protocol framework, recently released but developed over the last couple of years side by side with the WireGuard team, a lot of feedback from us. And we've written a custom implementation of one particular handshake of noise, which we'll go into later. Has a number of nice security properties. We have perfect forward secrecy. There's a new key every 2 minutes so that if the machine is ever compromised and the private keys are ever stolen, it's not possible then to go back in time and decrypt packets that used to be encrypted because the encryption keys for those have long since been forgotten. It avoids key compromise impersonation. This might be a new term to some of you. If you steal someone's private key, of course, then you can pretend to be them to everybody else. That much is plain. But many protocols have a flaw called key compromise impersonation, where if a private key is stolen, then the person who possesses it can impersonate anybody else to you, which is even worse. Because now not only can they authenticate on your behalf, but they can trick you into thinking that they're anybody else. And so the WireGuard protocol avoids this. We have identity hiding. So during all handshakes, we never transmit the long-term static public key in clear text. So for an eavesdropper who doesn't have either private key, it's not possible to figure out who's even talking to each other. So there's a degree of anonymity there, which is nice. Like all protocols ought to these days, of course, there's authenticated encryption. This means not only do we make the data secret, but we also ensure that it hasn't been tampered in transit. We have replay attack prevention, which turns out to be not completely trivial with this sort of thing because networks like to reorder packets. It's just a property of how networks work. And so we can't always rely on the next packet having, say, a counter that's definitely greater than the other. So we've got some classic algorithms with some improvements on them for keeping track of the last window of packets and making sure that they're never replayed. We have modern primitives. We use curve 25519 for elliptic curve Diffie-Hellman, which we'll go into. We use Blake 2S, a super fast hash function, SHA-3 finalist. We use Cha-Cha-20 and Poly 1305 for authenticated encryption, which again are state-of-the-art, super fast ciphers. And we use SIP-hash24 for hash tables. It turns out that ordinary hash table data structures are vulnerable to collision attacks if the attacker can control the input. And so SIP-hash is a nice, quick hashing function that's cryptographically secure. Now, going back to the point in the beginning about this being opinionated, we have no cipher agility. And to me, this is a feature. This is a good thing. We don't give choice. These are good ciphers, and if they're ever not good, then you'll upgrade your installations to a new version that has better ones. I don't ever want a situation where you have clients that are supporting partially the good one, partially the bad one, and then you have a sprawling mess of code and complexity to support these. And what's the point? Well, to support something that's not even secure anymore. Cipher agility, I think, too, is an idea that's best left in the 90s. So for WireGuard, we have a lack of cipher agility. Okay, let's get into the key exchange. This is a one round-trip key exchange. The initiator sends a message to the responder sends a message back to the initiator. Then from these messages, they do some computations to derive a pair of symmetric authenticated encryption keys, and then they can send their transport data packets, which are encrypted and authenticated. During this key exchange, they generate ephemeral keys. So we have the perfect forward secrecy. And the initiator and responder can change roles at any time, because if you look again, you'll notice it's just there and back. So it's totally symmetric. There's no requirement that one peer is always the initiator, or one peer is always the responder. They can swap around as they please. And invalid handshake messages are, of course, ignored. There's no, you did it wrong. You just don't get a response if it's a bad message, so that we ensure the stealth principle. So let's review Diffie-Hellman. This is quite important. We have peer A and peer B here. And first, peer A generates a private key. Say it picks a random number. Picks a random 32-byte string in our case. Then we derive the corresponding public key from that with some function along the elliptic curve. Then peer B does the same, generates a random private key, derives the public key. Now what Diffie-Hellman means is that if you take the Diffie-Hellman function of the private A and the public B, this will always be equal to the private B and the public A. I'll pause a second just to reflect on this, because this is kind of a remarkable property. And from this one relationship, this one function, we can derive some really neat protocols. So Diffie-Hellman of the private A, right, that's the top line, and the public B, which is the bottom line, is always the same as the Diffie-Hellman between the private B, which is the middle line, and the public A, the other middle line. And so this is what allows for generating what's called a shared secret without ever having to transmit the initial secret data, the private key namely, over the network. Okay, so as we said, one peer is the initiator, the other is the responder, but they can change at any moment. Each peer already knows each other's static identity, their long-term static public key. This is the equivalent of SSH's key. When you put in an authorized key, both peers know each other's long-term public key. But for each new handshake, we have a new ephemeral key pair, which is not long-term. This is the one that's forgotten every 2 minutes. And so the security properties of the WireGuard protocol is brought about by what's called the triple DH, the triple Diffie-Hellman, which amounts to a Diffie-Hellman between the ephemeral static, then the other static and ephemeral, and then the ephemeral. Now, because we want this to be a one round-trip protocol, we need actually authentication in the first message too. So we add on to this Diffie-Hellman between the two static keys, the two things that both sides already know about each other. So the first message, this is the message from the initiator to the responder. So as I mentioned, the initiator begins by already knowing the public key, the long-term static public key of the responder. And so the initiator sends the responder several things in one message. The first is a clear text ephemeral public key. So what it does for this is it generates the new ephemeral private key, derives the public, and it sticks it in the message in clear text. Next, it sends the initiator's public key, so its own static long-term public key. Except we don't want to put that in the message in clear text. We want to encrypt it so that we have this property of identity hiding. And so we use authenticated encryption using the normal ciphers as usual. And we get the key for that as an indirect result of this Diffie-Hellman, of the initiator's ephemeral private, the one that we just generated, and the responder's static public, the one thing we know about the responder. And of course, by the principle of the previous slide, that's equivalent to the responder's static private and the initiator's ephemeral public. So after the responder decrypts this part, then it knows who just sent it a message. It knows the initiator's public key. And of course, only the responder can decrypt this because only the responder has its own private key. The third thing in this message is a monotonically increasing counter, which usually is just a timestamp in, say, a format like TIA64N. But it can be any kind of counter that just always gets bigger. And that is encrypted, authenticated encrypted, doing the static Diffie-Hellman between the initiator's static public key static private key and the responder's static public key. And the reason we put a counter in there is to prevent against this message then being replayed. So we require new messages always to be bigger than whatever the previous one. And this mechanism doesn't require ever storing in any kind of long-term storage the most recent key, because in the worst case, it would be resent and it would just disrupt an existing session. But if the computer's been reset and the biggest one has already been forgotten, then there's no session to disrupt. So all we merely have to do is keep in memory the biggest number that's been sent so far. Okay, the response to that message from responder to initiator is a little bit simpler. So when the responder receives the previous message, it learns the initiator's static public key and the initiator's ephemeral public key. So now the responder can generate its ephemeral key. So it first puts that again in clear text as the first part of the message. Then it encrypts an empty buffer. So in other words, it authenticates an empty buffer using a key that's an indirect result of the two remaining Diffie-Hellmans. The first is between the responder's ephemeral private, the one just generated, and the initiator's ephemeral public, which it just learned from the message. And it uses the responder's ephemeral private, again just generated, and the initiator's static public, just received from the message. And so when the initiator, when the responder sends this, it'll verify to the initiator that it can decrypt that message. Okay, so to recap, in the end we get some state, some shared variable that's a result from those four Diffie-Hellmans, the triple DH plus the static. And from these then we can derive a pair of symmetric encryption keys that then we use our cha-cha-20 poly1305. And so we do session derivation using a conservative KDF function called HKDF. And then when the initiator sends its first data message using this, then it confirms to the responder that in fact it could decrypt that message. Okay, so this might all seem a bit complicated and overwhelming, but in fact it's really simple in the end, at least compared to SSL or IKE or any of those. We use very simple set of primitives. We have elliptic curve Diffie-Hellman, we have hashing, and we have authenticated encryption. That's it. So with those three primitives, we have a key exchange. And the lines of code for the implementation, I wrote this in 441 lines of code. Compare that to 500,000 lines of code in OpenSSL. So it really makes a big difference here. And again, there are no certificates, no X509, no ASN1 parsing. So with super small surface of attack, it should be a lot more dependable. Okay, so this goes back to what we spoke about in the beginning, that WireGuard appears stateless to the administrator, but like any secure protocol, some state is needed. What we've done here is defined a very simple state machine such that we can prove that every transition between all possible states has been accounted for. There's no undefined possible transition in it. So we can prove that, at least in theory, it's bug-free. And then, because the implementation is so simple, we can check those against each other and be reasonably assured that it works well. And so it's event-based, and we have 4 basic events. User space sends a packet. When this happens, if there's no session established for the last 120 seconds, we just send a new handshake initiation to get a new one going. If we don't receive a response after 5 seconds, then we just send another initiation. After we successfully authenticate an incoming data packet, we might have another packet to reply, in which case that's fine. But if we don't have anything to send back, after 10 seconds, then we'll just send an encrypted empty packet so that both sides know that they're still talking to each other. Then the other side, if it doesn't receive any packet at all after 15 seconds, it knows that something's gone wrong with the handshake and it reinitiates it. And of course, again, if no sides are talking to each other, if they both stop talking, no packets will be sent at all. So a very simple set of timers, but it enables us to make the interface completely stateless to the administrator. Okay, the last security principle that we'll talk about, and a very important one, the subtle thing to get right, is denial of service resistance. So hashing and symmetric crypto, they're both very fast. The ciphers are optimized, they work well on CPUs, but public key crypto is slow. Even Curve 25519, which is among the fastest elliptic curves for this sort of thing, even that is slower than, say, a gigabit network interface, which is a problem. And so traditionally in these protocols, you can launch a denial of service attack against a machine by just making it do tons of public key crypto operations. I think SSL even is vulnerable to this in certain cases. You can make SSL do tons of RSA computations and easily DOS a box. And UDP makes things difficult because it's hard to get IP address attribution directly with UDP. And so WireGuard makes use of cookies to solve this. So let's review short history of denial of service attack cookies. Okay, cookies that are TCP-like. The dialogue is like this. The initiator says, compute this Diffie-Hellman. The responder says, your magic word is Karage. Ask me again and tell me the magic word when you know it. And so the initiator said, okay, my magic word is Karage. Now will you do it? And finally, it does the Diffie-Hellman. And so this will prove IP ownership since there's a protocol back and forth. But we violate our security principle because now we have to store as state the fact that Karage is associated with this IP address. And this always responds to messages, so we violate our stealth principle. And of course, the magic word can be intercepted. So this doesn't really work well for a robust and secure solution. Then we have cookies that are DTLS-like or IKEv2-like. And the dialogue is a little more sophisticated. It says, compute this Diffie-Hellman. The responder says, okay, my magic word is some big hash. Ask me again with the magic word. And the responder says, okay, the magic word is that big hash. Now will you do it? And it turns out that the big hash is a MAC, some sort of hash, a keyed hash, which uses as its key a value that's secret only to the responder and rotates every couple minutes, and as its payload, the initiator IP address. So this way, the responder doesn't have to store that state, since you can just rehash against the IP address using its secret and see if they match. So this is nice because it's stateless, but again, we always reply to the message. And so we violate our stealth principle, and of course the magic word can be intercepted, which is a problem. And finally, a more subtle point commonly overlooked is that the initiator himself can be denial of service attacked by just sending the initiator a bunch of replies, your magic word's this, your magic word's that, over and over, and it'll never get the magic word it wanted. And the reason this is often overlooked is because we tend to think in the client-server architecture, where the server is the thing we want to protect. But in WireGuard, we do away with that. We just have one peer and the other peer, symmetric roles. And so it's really important that neither initiator nor responder can be denial of service attacked. Just as an aside, host identity protocol and Bitcoin have kind of a similar set of ideas, but different approach. Initiator says, compute Diffie-Hellman. Responder says, well, mine a Bitcoin first, then ask me. The initiator says, all right, I toiled away, I found the Bitcoin, now will you do it? So the proof of work, in other words. And this is good if the puzzle is harder than Diffie-Hellman, because it perfectly solves the denial of service. But again, it doesn't work for the symmetric roles of the initiator and the responder. Because say now you have a server that has to do this computation for tons of clients, well, it's unscalable. Okay, so the WireGuard variant builds on top of the DTLS variant, but adds quite a bit to it, fundamentally changes it. So each of the two handshake messages, the initiator to responder message and the responder to initiator message, has two MACs each, MAC 1 and MAC 2. So MAC 1 is calculated as a hash of the responder's public key concatenated with the prior contents of the handshake message. And so if the MAC is gone or invalid or missing, then the message is ignored. If it is there and is valid, then it means that, okay, the person talking to me knows who I am, knows that I exist here on the internet, so that then we can safely respond to this without giving up our stealth. So if the responder is not under load, if it's not under denial of service attack, if it has plenty of CPU, then we proceed normally. Then we don't need to do any denial of service protection. But if it is under load, if the CPU is maxed out, then instead of responding with the second handshake message, we send back a cookie. Only this time we don't send it in clear text, we encrypt the cookie. So first, let's talk about the payload of the encryption, which is the cookie itself, is right there where we have a MAC of the initiator IP address using a responder secret that changes every couple minutes. This payload here is essentially the same idea as the DTLS and IKEv2 style cookie. However, it's encrypted using what's called an AEAD, authenticated encryption with additional data. So there's encryption, which is just making the data secret. There's authenticated encryption, where we ensure it hasn't been tampered with. There's authenticated encryption with additional data, where we add to that authentication some other piece of data that both sides have, but that isn't necessarily transmitted. So first of all, we set as the key to the encryption a hash of the responder's public key concatenated with a salt, so that the message itself can't be read unless someone already knows the public key of the responder, in which case the attack model goes away anyway. Then as the additional data, we give it the byte content of the original handshake message itself, so that that reply is always tied to the message that caused that reply. So this prevents against the denial of service attack against the initiator. So then when the initiator gets this, it decrypts it, it then has the cookie, and it calculates MAC 2 as just a MAC over the handshake message and using the cookie as the key. And if it's valid, the message is processed even when the CPU is maxed out. Okay, so then all of this gives us essentially IP attribution. We know definitely that that IP is talking to us. And then we can just use ordinary token bucket rate limiting, the usual network rate limiting algorithms that you have in web servers and every place else. Tons of literature on it, tons of implementations, nothing fancy. But in doing this, we maintain stealthiness, which the other ones lack sorely. And the cookies can't be intercepted by someone who couldn't already start the same sort of key exchange. And the initiator, as we said, can't be DOSed because of this additional authenticated data. Okay, performance is extremely good. Because we're in kernel space, because it's a part of the Linux kernel, it's really fast and it's low latency. We don't need to copy packets back and forth to and from user space. CHA-20 Poly 1305 is super fast on all hardware, and it's safe to implement on almost all hardware. In contrast to, say, AES. Now, AES-NI, the native instructions for AES in processors like Intel and ARM, is fast too, obviously. But in fact, as vector extensions in processors get wider and wider, Cha-Cha is already competitive now with AES, even using AES-NI. And Skylake was released recently, new Intel platform with AVX512, super wide instruction, which makes Cha-Cha 20 even more competitive against AES. Secondly, AES is really difficult to implement without some sort of specialized hardware that's both fast and secure, that is, avoids against cache timing attacks. Because of the lookup tables, just the nature of AES is notoriously difficult for this. But Cha-Cha 20, can be really fast on general purpose processors. Even small microcontrollers are decently fast. And it's safe. The almost naive implementation of Cha-Cha is pretty safe. It's not that difficult to implement. And in general, since WireGuard is less than 4,000 lines of code, there's not a lot of overhead. There's not a lot happening now. Less code, does that mean a faster program? Well, not always. But in this case, where you're comparing 500,000 lines of code of OpenSSL and 4,000, I think it's a pretty good bet that, well, it's going to be a lot faster because it's just less is happening. So if we look at the performance measurements, indeed, it beats the competition pretty well. Even IPsec, which is a pretty optimized code base, we're both higher performance and lower latency than the competition. And this is really before the implementation efforts have gotten into intense optimization. So I think that margin will only increase over time, in fact. Okay, so just to recap, again, less than 4,000 lines of code, so everybody in this room who knows C can read the entire code base in a sitting and find bugs or fix things, or at the very least become assured yourself that it's code to rely on in critical infrastructure. The general design of it lends itself to be implemented with pretty basic data structures. There's not a lot of state kept, and when it is, there's no dynamic allocation. We don't modify state in relation to unauthenticated packets, etc. As we said, it's extremely stealthy. The config is minimal and stateless, and we have our crypto key routing table sort of smoothing the problems when we get rid of the layers, and we just have our basic network interface. And as we just said, best-in-class performance and very opinionated choices. So I'll just show you a quick demo of what it's like to configure such a thing. Let's see here. Okay, so we have peer A and peer B, and we generate a private key on each, WG gen key. And as you see, private keys are super small. You can copy and paste them. And public keys are derived from the private keys. And so each one now has a private key. On peer A, we add an interface using normal IP route 2 standard Linux tools. We add an IP address to it. Again, pretty uninteresting, normal thing. We just set up an interface. But then we have WG for giving it the WireGuard specific information, like the private key. So we set the link up. Now we can do the same thing over on peer B. We'll add the interface, give it an IP address. And again, because it's just a normal interface, it integrates with all the things you already know about. And WG, hopefully at some point, will be integrated into the IP command, and it'll be even closer to what you already know. So when we hit IP address, we can see we have various interfaces, local host. We have ETH0, which is our internet-facing interface, one on each, with just an RFC 1918 address. And then we have our WG0, which is our WireGuard interface, one on each peer, which again is just a 10/8 there. So now we can actually tell the peers about each other so that they can speak to each other. So there you see we have the public key and private key for each one. And so in peer A, we're adding peer B's public key and giving it the allowed IPs as part of the crypto key routing table and its internet-facing endpoint. Then peer B will do the same thing. We get the public key of peer A, we paste it in there. We give it the allowed IPs that that peer is allowed to have and the internet-facing endpoint. And as I mentioned before, all of this you can configure in a configuration file. You don't have to type it all out in the command line. And the tooling is starting to be integrated in other networking tools too, which is quite nice. And then we just ping, and then it sends it securely over the network. And that's it. It just works. Okay. Okay, so that's it. If you want to learn more, WireGuard.io is the website, and there's tons of documentation, source code. There's even a demo server that you can send packets to and tunnel internet traffic. You can try and attack it if you're curious to see how it withstands things. It's my website, my company's website, Edge Security, and please join the mailing list and contribute. So I'll open it up to questions in the remaining 2.5 minutes or so, if there are any.
So very interesting tool. As someone who's set up open VPN terminals before, I totally understand the pains that you went through to create this. Now, I'm not sure I really understand the whole stealthiness. Like, as a network administrator, how am I supposed to troubleshoot that I'm unable to connect to that remote endpoint?
Well, if you're a network admin, I mean, you can look at the packets going back and forth. And if you're sending a packet and you don't get the one reply packet to it, then you know it's not working.
But I don't know where it's not working, right? I don't know if the host machine received it but didn't respond. I don't know if a gateway blocked me. So not having, like, okay, let me ask you this. What is the benefit of having the stealthiness?
The services aren't enumerable by attackers. So I come from an offensive perspective, and first thing I usually do is scan the networks, see what systems are out there, see which machines are on the edge that I should attack, and then I go in that way. Mm-hmm. With WireGuard, if you put WireGuard on your outermost edge machine, an attacker can't even see where to begin.
Okay, thank you.